In the next few minutes, I'll show you what an embedding actually is, how a sentence gets turned into a list of numbers that captures its meaning, how similarity becomes geometry, why almost every AI search and recommendation system you've ever used is powered by this one idea, and what RAG really is once you strip away the buzzword. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into embeddings. Last episode we left off here. Your prompt gets chopped into tokens, and each token is mapped to a single integer ID. But the model doesn't actually work on integers. The very first thing it does with those IDs is look each one up in a giant table. That table is called the embedding matrix, and what comes out of it isn't a number, it's a list of numbers, a vector, typically somewhere between 300 and 4,000 numbers long. That vector is the token's embedding. It's the model's internal representation of what that token means, not as a definition, but as a location, a point floating in a very high-dimensional space. Here's what one embedding actually looks like. The word cat, run through one of OpenAI's embedding models, comes out as a list of 1,536 floating point numbers. You, a human, can't read this. There's no dimension labeled furry, no dimension labeled mammal. The axes were discovered by the model during training, and they don't correspond to any word in any language. What matters is not the numbers themselves, it's the relationships between them. Because once every word and every sentence lives in the same space, you can do something powerful. You can measure distance. And distance in this space means something very specific. It means similarity of meaning. Once text is embedded, you compare meanings the same way you'd compare two arrows pointing out from the origin. The metric almost everyone uses is called cosine similarity. It's the cosine of the angle between two vectors. If two vectors point in nearly the same direction, their cosine is close to 1. If they point in completely different directions, their cosine is close to 0. Dog and puppy land at about 0.9. Dog and cat, both pets, both four-legged, land around 0.76. Dog and automobile land at 0.18. Dog and the word the, which carries almost no meaning on its own, lands near 0.07, one number. That's the entire comparison. No neural network call, no generation, no API, just a dot product between two lists of numbers. Here's the moment that made researchers realize this wasn't just clever indexing. If you take the vector for king, subtract the vector for man, and add the vector for woman, the point you land on is extremely close to the vector for queen. Paris minus France plus Italy lands on Rome. Walking minus walk plus swim lands on swimming. The space doesn't just know which words are similar. It's learned that certain directions in the space represent consistent relationships. A gender direction, a capital of country direction, a verb tense direction. Nobody programmed those axes. They emerged because the model trained on billions of sentences where those relationships hold. Meaning in this space became math. So what do people actually do with this? 4 things, over and over. 1. Semantic search. You embed a query, you embed every document in your library, you return the closest ones. No keyword overlap required. Search for how to fix my bike, and you'll find an article titled Repairing a Bicycle. 2. Recommendations. Netflix, Spotify, Amazon, every more like this feature you've ever seen is embedding your items and finding neighbors. 3. Clustering. Dump 10,000 customer support tickets into an embedding model, cluster the vectors, and the clusters are basically topics, without a human ever labeling anything. And 4th, the biggest one, the use case that has a buzzword on it, RAG. Let's talk about that one. RAG stands for Retrieval Augmented Generation, and it's the pattern behind almost every AI chatbot you've seen that answers questions about specific documents, a support bot that knows your company's help articles, a legal tool that cites case law, a coding assistant that knows your internal codebase. The recipe is 3 ingredients. 1. Take every document you care about, chop it into chunks, embed every chunk, store the vectors in a database. 2. At query time, embed the user's question and retrieve the top few chunks whose vectors are closest. 3. Paste those chunks into the prompt and ask the model to answer using that context. That's it. The model isn't smarter, It just has the right page of the manual open in front of it. Every Chat Your Docs product on the market is some variant of this pattern. Embeddings come out of dedicated models that are separate from the big chat models. They're smaller, cheaper, and much faster. OpenAI has Text Embedding 3 in two sizes at about 2 cents per million tokens, basically free compared to generation. Voyage AI, which Anthropic partners with, often tops the retrieval benchmarks. Cohere has an embedding line tuned for enterprise, and there's a thriving open source scene. Models like BGE, E5, and Nomic, all free to run on your own hardware, all benchmarked against each other on a public leaderboard called MTB. For most apps, you pick one, stick with it, and you don't have to think about it again, because mixing embeddings from different models in the same database will break everything. A few things catch everyone the first time. 1. You can't mix embeddings from different models. A vector from OpenAI and a vector from Cohere live in different spaces. The numbers look identical, but they mean nothing to each other. Pick a model at the start, and if you ever want to switch, re-embed your whole corpus. 2. Chunk size quietly decides your retrieval quality. Too big, the vector averages out and you lose the specific thing you were looking for. Too small, you return a snippet with no surrounding context. 3. Embeddings are bad at negation. The sentence, "This product is not helpful," embeds very close to "this product is helpful" because most of the words are the same. 4. A general-purpose embedding model on a specialty domain, legal, medical, code, will retrieve worse than a model fine-tuned for that domain. And 5. The model's sense of meaning is frozen at the moment it stopped training. New product names, new slang, new acronyms, it has no idea. Every team that ships a serious retrieval system ends up in the same place. Pure embedding search isn't enough on its own. The standard fix is called hybrid search. Think about a support question like this one. Can't reset password. Error pull 401. An embedding-only search finds articles about logins and passwords, but it'll miss the fact that the ticket contains a very specific error code the model has never seen. A keyword-only search finds the error code, but misses the user who writes, "I can't log into my account," and means the same thing. Hybrid search runs both in parallel, an old-school keyword search, the kind Google was doing in 1998, and an embedding search. Then it takes the top 20 from each and re-ranks them with a slower, smarter model called a cross-encoder. The cross-encoder looks at the query and each candidate side by side and scores them properly. Almost every production RAG system you use is running some version of this pipeline. Pull back and you'll notice something. Almost every AI product that isn't just a chat box is an embeddings product underneath. The chatbot that knows your documents, the support ticket router, the duplicate question detector, the semantic search bar, the more like this recommendation. All of them are doing the same thing, turning text into vectors and measuring distance. If tokens were the atoms, embeddings are the periodic table, the structure that lets you compare, cluster, and retrieve anything against anything else. Once you see the pattern, you'll see it everywhere. That's the end of this concept. But each video stacks on the last. Subscribe and we add the next layer tomorrow. New videos every day on the AI concepts you keep hearing but nobody defines cleanly. Tomorrow, vector databases, the infrastructure that makes all of this actually fast at scale. Thanks for watching.